All right, hello everyone. We are going to do another layer of discussion about multi-computation and lazy functions. And Nick has, we sort of decided we weren't going to have a generic lazy expression, but Nick has been investigating that and has interesting things to talk about here. So go ahead. Why don't you do your demo? Explain what's going on.
So, well, first of all, so the motivation for this thing was to actually develop something that's not just immutable expression that is in some way lazy, right? Because it was kind of hard to program with it when you actually have to have some cache and things like that, right? So I tried to make this general thing like an expression within some sense have this mutability property. So
Which expressions do not have?
In general, yeah, all of the expressions are immutable.
Right. But somehow lazy expressions, the idea is that they're not immutable.
Yeah, I try to make them immutable and see what it's gonna lead me to.
And
you mean you try to make them mutable?
Yeah, mutable. The lazy expression is a mutable thing. So it's like some bunch of dynamics around it, also like visualization. So
sorry, just to clarify, is it visibly mutable, or is it just mutable in secretly in order to do caching and stuff?
It's very visibly mutable. That's the idea. It's like I'm gonna show you right now.
Right.
This is like represents a mutable expression, which is also lazy. So just contains some kind of code that you can evaluate. So like this is like you can click around it, it evaluates, right? You can click like some inner expressions, you can evaluate them in a way, and it's mutable in a sense that it actually propagates for whenever it appears, right? It's like triggers all the dynamics and actual structure. When I have this lazy expression later on, it's still the same kind of thing. It mutates.
Okay.
Right? If you construct it from scratch, it's another one. There's a possibility to cache it. If like I can turn on the cache, and if I construct the same expression again, it's going to link to the same kind of thing. And if it's already been evaluated, I'm not going to evaluate it twice again.
Okay. All right.
So
okay.
that's a possibility. And you can like, maybe if you have a separate one, if you like
what are
look
the two arguments to lazy expression?
This is like an actual symbol that is assigned to. No, it's like in order to make it mutable, I can talk about how it actually implemented. It's like assign the symbol, this data structure value, right? If you make this thing, now it links to this value that is immutable.
Okay, but hold on. So if I say lazy expression 1 plus 2 times 3 comma b, that is a different expression from 1 plus 2 times 3 comma a. Is that correct?
Yeah, that's going to be a different one.
Okay, so that's like it's like there's the content and there's some kind of tag that indicates
that tag or reference. If we don't provide a second argument, it's going to be like some unique symbol. You can see it's like ref $114 there. If I provide it, it's going to be tagged with A. If I make it the same one again, it's going to try to assign to the same thing, but it basically can't assign it anymore. So I have to make it like reference it.
All right. Well, keep going because we're not so far. I don't really understand, but go ahead. Yeah.
Okay. So what other things like? Well, we are pretty much already showed you how to reference each other. If I make a bunch of these lazy expressions, well, first of all, if I construct a one lazy expression like x here, and then use it within other expression, it kind of propagates itself up, right, to construct a new lazy expression. So we can have like nested things that reference each other, right? So you construct an
What
x.
do the dotted lines mean?
Dotted lines is like it's possible to evaluate them. It's not a lazy reference inside of it, but some kind of sub-expression with value q. Basically, you can just evaluate it, and it's going to like evaluate in place.
Okay.
You can like construct a bunch of things that reference each other. There's like limitations that they have like built in that it's not looks within some like 2 levels deep into the formatting. So, but I can, like, I don't know, make very deep evaluation.
What the heck is this? I don't understand this at all.
Well, dynamics is pretty crazy looking. It's like this represents a self-reference. So basically, if this is the lazy expression, this is the thing where it's reference itself.
I like the use of the emoji for that.
Yeah. Why not to use it? So this represents some different reference, like maybe this one, right? They're all dependent on each other. Why it's like now you can even build a graph of references. So you can ask for any of those lazy expressions, and they will evaluate enough to see what reference it contains and see kind of this dependency things.
And can you click on them inside the graph?
Yeah.
Just for maximal insanity. Oh my God. Okay.
Yeah, they're crazy. Yeah, so yeah, maybe I will generate them because they like reference each other. They can expand exponentially. Look, I'm gonna look crazy. So this is kind of, if anybody familiar like with Haskell programming, they have this lazy, non-strict semantics of evaluation, and they have lazy expression is essentially a func. It's some kind of code reference that lives in a heap that you can evaluate, right? And what forces an evaluation in such kind of languages is pattern matching. As soon as you pattern match against this func or lazy expression, the parts of it that only sufficiently to pattern match against it are going to be evaluated. So it's like if you create some kind of expression like this, right? It's not evaluated anything yet. I can ask whether it's a list or not, right? You can tell you, yes, it's a list. And nothing in this expression being evaluated to answer this question. I can ask whether it contains plus or times here. It's still evaluated nothing. But as soon as I ask for something like to check whether this first element of this list is integer, it would force evaluation of this particular thing. So now it becomes like evaluated.
So it's a pretty bizarre idea here. I mean, the claim is there is an expression and it can be in its unevaluated form, or it can go through and be evaluated. So for example, let's say that my match was, it's a thing of length 2. Okay.
Yeah.
Then in its unevaluated form, it could be, let's say, it's a thing of length 1. Okay. Because in its unevaluated form, it says range of 1,000. And that's a thing of length 1. But range of 1,000 is also a thing of length 1,000. So which one is it? See what I'm saying?
Well, if it's a range, if it's a lazy range, it will evaluate enough to answer this question.
No, I know that, but I'm asking the question. Range of 1,000. At some level, that's of length 1, but at some level, that's of length 1,000. So is it the case that when you are defining these things, that what you mean is that the pattern matching is as if it is fully evaluated? Is that correct?
Well, in what sense this is length 1? I don't understand. It's like,
look at the original expression. Range of 1,000. It's length 1. As a pure, in the same sense.
It checks the head. You can check the head. It's like,
look, no, but I don't understand. In the same sense that 2 plus 2 is underscore plus, matches underscore plus. 2 plus 2 no more matches underscore plus than range of 1,000 is of length 1.
Well, if you had this kind of pattern, then yeah, in order to answer this kind of query, you have to evaluate the range.
No, but look, underscore plus is matching the unevaluated 2 plus 2.
Yeah.
Right? Why are you allowed to match the unevaluated anything? Because if you can match unevaluated things, then range of 1,000 matches a thing of length 1. Go ahead.
If you do length of unevaluated of range of 1,000, that gives 1, right?
Yes.
No doubt it does.
Although it's unclear. I mean, if you did this in general, it's unclear what you would, what you'd actually feed into the X so that it would, you can't just do hold of the expression because it might, that's not the same as the expression. So there's kind of nothing you could put in there that would actually
Exactly.
work
But
with
what I'm
functions
claiming
like
is
length.
semantics is not properly defined. What I'm claiming is there is a semantics that is pattern match against the fully resolved version of this currently lazy expression. You see what
Well,
I'm
the
saying?
semantics is like you structurally look at the expression. If the head doesn't match, you fully evaluate it.
That's not reasonable. It's not going to work. It's mushy, right? Because, it's one thing to say the pattern match is against the final unlazy, eagered form, right? Which you may or may not actually generate. That's up to you whether you actually generate it. But the semantics is the pattern matching is against that, or the pattern matching is against the thunk generator, which is quite different. Am I making sense?
Well, if you have like lazy expression with it still can contain func generator that generates a list. I can't quite get it.
No. Do you understand what I'm saying? I'm saying you can't have it both ways. You can't both match. If 2 + 2 is the lazy expression, that cannot be matched to underscore plus. You see what I'm saying? Okay, so now if you say match q of that, comma, underscore plus. Okay, I think that's just wrong. %72. Okay, so if you say match q of %72, comma, underscore integer. Underscore integer, yeah, okay. Okay, I claim both these cannot both be true. I claim that's just going to blow up the world to have both of those be true. It's either one or the other. It either has head plus or it has head integer. Can't have both heads. See what I'm saying?
Well, sure. Well, that's because we dealing with this mutable stuff.
It's not because it's mutable. It's not because it's mutable. It's because it's not properly defined semantics. I mean, it's either, look, those two lines are inconsistent.
Right. I mean, really, it should just say it matches lazy expression. I mean, what happens if you say head of %72 anyway? Because normally head of hash equals
make a new
blah
lazy.
is equivalent to match q of it, comma, underscore blah. Oh my God. Okay.
Wow.
So does it consume absolutely everything, or could you say something like hold? Is there anything?
Well,
No, it
obviously
clearly doesn't
you
consume
can
match
hold it.
q, does it? Because you can see match q just worked on the match. It didn't just
Right.
the match q.
Well, for match is a special case. It's like the
Arg!
up value for lazy expressions.
What's
Okay.
that?
There's
It
an
has an
up
up
value
value
for
for
lazy
match
expression.
q. Yeah. What has a match q? It has an up value for everything, but it has a special up value for match q.
Yeah.
Which
Exactly.
yeah.
And also replace at this point. But yeah.
Color me unconvinced here.
Does that mean that you can't put a match q into the lazy expression directly?
Well, you can try it. In this way, if you want to like have a benefit of this automatic up value, then you can. But you can obviously make a lazy expression and just put match q inside.
Okay, all right. I'm just not convinced by this, but keep going because let's understand what you figured out about lazy expressions in general. So keep going here.
Well, and then, well, after building this kind of crazy thing, I try to revisit lazy lists again, but using this kind of technology or whatever. So I have to reinvent this kind of lazy range thing. I'm using a different constructor now because I still using the same old bucket. So the lazy range with immutable lists is still there. So I have to use a
By the
different.
way, presumably if you clicked on these little dotted areas in the wrong order, you can just make it totally explode, can't you?
Sure, but that's like leading towards multi-computation. You can evaluate in whatever order you want.
Well, right, except that this program, presumably cares that it be evaluated in a sensible order.
Yeah. So there's some default semantics how lists should be evaluated. For example, right now it's always evaluates the first element that contains some kind of not evaluated code, and ignores what code if there's anything after that. For example.
Okay, so I need to understand something. So there's multiple things going on here. So one thing is this idea of the partially evaluated expression where you can control the evaluation path by clicking. Right?
Yep. Right.
And so imagine that this was a proof. Okay, and imagine that you were, imagine this was kind of like almost a proof assistant type situation. And
I think it would be like at least some typing would be required in order to actually make it useful for proof assistance. Especially if you think about something like proof assistance and lim. If any of those lazy expressions has actually some type assigned to them, then it would be exactly like in any strictly typed language.
Okay, but I mean, what we're looking at here, I'm a little bit confused here. So we can imagine, forget the proof thing for a second and just talk about, evaluation in the sense of Ian's evaluation graphs, trace graphs rather. This thing could represent okay, in a trace graph, what is this? Is this a transversal of a trace graph? What is this? What is one of these objects? Is it a slice at one level of a trace graph where you can then say, I will click something to follow an edge in the trace graph? Is that right, or is that not right?
Yeah, it's kind of close. If you have a multi-way version of the trace graph, you can, when you have an option to go in either direction, and not just following default evaluation.
No, I understand that. So I mean, but you're saying, right, and you click and it follows a time-like edge. Is that correct? There could be multiple branches, but every time you click, you're following a particular time-like edge to another state. Is that right?
Yeah, but in this case, it's also a mutable state. Well, this is just for performance reasons.
I'm sorry.
Can
Go ahead.
Can I ask, is when you click, does that do a single evaluation, or is that like an infinite evaluation to a fixed point when you click on something?
Well, if you have like a definition like this, then it's just one. It tries to do one evaluation as much as possible. If there's some explosion going on underneath that I can't control, obviously it's going to explode. Lazy range is defined. Like,
sorry.
So you can see the definition of the lazy range. For example, the laziness comes because it explicitly generates expert struct there. So that's what stops it, even though it's recursive. That's what stops it to go infinitely.
Could we see x equals x plus 1, or does that not make any sense?
No, we can totally do this. It's like there's like different buttons I'm clicking. There's like one for evaluation and one to evaluate references. Like I can just evaluate.
What? Go ahead.
Oh, you're not just clicking. You're pressing a key or something.
Yeah, like option key. If I press option key and then click it, I can evaluate only the reference.
Really quite crazy, but
I can do this like this.
Oh my god.
What? That okay? Could you go back to
what does lazy expression of x equal x plus 1 do?
I mean,
Like I see
but-
this is like a self-referential thing, but what like on a separate input, do lazy expression of x equal x plus 1?
Well, this is well. First of all, this now is just a hold of this x plus 1. The dashed box says that there is a value assigned to x, so this is itself can evaluate. As soon as I evaluate it, it relates to the lazy expression again. So that's why it's
Okay, so
shows
click it.
as a reference.
Wait, what does that mean? What does that emoji mean?
It means that this box, it has a reference, and this is this sub-expression references itself. It's like this ref.
The emoji represents the whole expression. It presents.
Yeah,
It represents %79 kind of thing.
Okay. All right. So click something once to go one level more level. So I want to see, it should be blah +2 or something. Should be something you can get.
Well, if I just click on the box, I can evaluate this expression just with the, treating all the references inside or any lazy expression as a symbol, purely symbolically, right? In this case, it's gonna maybe like just sort it because plus is orderless.
Okay, so then what? Click it again.
If we click it again, nothing happens already. I have to resolve the reference, right? As soon as the reference is resolved, it's like once I get the same expression because it's mutable. It's already mutated, so it's like a new one.
Okay, well, so do it again. Click it again. Why did that go 3? Did you click it twice then?
No, I clicked it once because there was one reference that referenced itself, but it was referencing the mutable thing. So it's kind of like
it added another layer of the already mutated thing, not the original thing it started with.
That's like if I resolve this reference again, there's gonna be 4 more ones again.
Show me. Because that self-reference is to that whole thing with 8 ones now.
Yeah, to the whole box with not dashed.
Okay, now how did you resolve the ones? Can you now resolve the ones somehow?
Yeah,
I
just click on the whole expression. I click on the whole expression where the reference just treated as a symbol.
Okay, I don't understand. In terms of evaluation, trace graphs and so on, what did you just do?
I just evaluated the outermost expression. And that's it.
Okay. Okay. All right. Can you just do x equals lazy expression of list x comma x and see the tree version?
Okay, tell it again. What?
X equals lazy expression of list x comma x.
X comma x?
Yep. Binary tree.
Yep.
Okay, so okay, now how do I go one more level there? What did you just do? What did you click? Did you click the same thing or you click a different thing?
I clicked on I resolved the reference, the left one. So
could you start from the beginning again here, just to reevaluate that?
So evaluate this one.
What did that do? What did that do?
It evaluated x itself, because x is just this lazy expression, and a lazy expression reference. It's
okay. And then when you evaluated it, it said, "Now I'm a reference to the whole of the self."
Yes.
Okay. All right. Now click it again.
Now, if I just click it, nothing happens. I have to click it with the option key or something.
What's the option key doing? What's the option key
Well,
doing?
just for convenience, there's like 2 axes that I can evaluate. Either just evaluate an expression or I resolve the reference, just for a better control of this thing.
Okay, so wait a minute. So resolving, okay, in that expression, the first boxed x, how do you resolve its reference?
Like this one?
Yes, that one there.
Well, just evaluate this expression on any level.
Okay, no. That in and of itself, you just click it. Is that right?
Well, yeah, I can click it either
just
inside
click
of this box.
No, okay. Just click it. Okay, that does that. That's what I expected.
Sure.
Okay, now if you click inside the box, that left box, what will that do? Will that resolve anything or not? Or are there no references to resolve there?
Well, there are references, but there's nothing to evaluate. It's not evaluate. So I'm clicking right now. It evaluates this without resolving these self-references. So it's not doing anything. But,
Okay.
but I can resolve any of those, or both of them together. And it's gonna like splice the whole outer box in place of those.
We'll show it. Oh, for God's freaking sake. What is this doing? Okay. So every one of the self-references was now replaced by the current state of what that outer square box was, outer filled box was.
Yep.
Okay. All right. Well, you've got a couple more demos to show there, and then I want to go back to what on earth this all means.
Yeah. No, that's like classic. Oh, this is basically the same thing as above, but this is a few version of obligatory Fibonacci ones. They're gonna be like crazy. This is one very explosive, and it's like this one is less explosive. I know what's beeped there. I know what's going on. Something broken. Is it? Oh, it's probably a problem. It's because we created a reference above.
Okay. So let's understand the bigger picture here. Okay. First question is, how is this relevant? Okay. Our original objective is to represent multi-computation.
Yes.
Is this relevant to that?
Well, I think it is.
The main thing that you're introducing here is this notion of a self-referential structure. Is that correct?
No, it's not the main thing. It's references in general. There's some code expressions, and I can reference them and mutate them. Not just self-references.
Okay, let's review where we were at before. We have a concept of lazy list. We understand that there are operations we can do, and then at the end we resolve it. How does this relate to that?
Like before, before it
Right,
was
so
looking
you have
like
lazy range. I don't know. Okay.
it was like this before.
Yes. And now we say on that lazy range, let's just remind ourselves what we do. We are able to say in lazy range, select prime queue of cache and even queue of hash on the lazy range. Okay, now what happens here? Okay, now, so now how do we resolve this? The thing you just gave there, how will we resolve that?
Hold on, something broke.
Oh,
Yeah, let me kill it. I just modified something, so I'm not sure what.
okay. Okay. It's not obvious that can work. I mean, it's not obvious because it doesn't need to prove a theorem, basically, to make that work, to resolve that to 2.
Yeah, it should. Well, that's why it's kind of stuck, because I pressed the infinite evaluation one. It's like,
I see. That's hopeless. Yeah. So, I mean, if we just say, in that ampersand, say ampersand hash less than 1,000 or something, just to make it.
Maybe like this.
Well, and hash less than 1,000.
Well, that would be
Trivial. Well, that's okay. Now that should resolve completely. Keep pressing it because now it should just resolve.
No, I'm not sure about that.
Oh, it still can't resolve. I see. It still can't resolve because it doesn't even know. It doesn't know what's going to be in the lazy range. Fine.
Yeah.
Fine. Okay.
Yeah. This is...
So we have to go to a meta level to deal with this. That is, we have to go out to the operating system and kill the process.
Yeah.
Huh. Okay. All right. So let's go back again to remind ourselves what we're trying to do, right? The real objective, which we don't seem to be following here, which we really need to follow, is the implementation of multi-computation. I've said this, many times, replacing our multi-way functions with something else. Is what you're doing here contributing to that or not?
Well, if you consider multi-way system is like what multi-computation is, to not really. This tries to be, something more general.
Okay, well, let's try to understand what it is. Okay.
So yeah, so like I see it's like we need some ways to define a bunch of semantics of how we compute stuff. Not just evaluating outermost expressions like that, even lazy or not, but in general, any kind of evaluation technique, somehow customizable and controllable.
Well, and by controllable, we mean you press things and random things happen, and sometimes you have to go out to the operating system to kill it.
Well, pressing, just making a nice formatting is just a nice visualization, but it's not the point, right? It's just to make better make sense of it.
No, I understand, but I'm trying to understand. Your concept here is usually the overall sort of prime mover of everything is the evaluator. That is, in the language, in the standard situation, is there is an expression, every time it's presented, the evaluator takes a crack at it and does something to it, right? It's kind of like in the universe or something. You can imagine it's like there's a thing that's just apply the rule, apply the rule, apply the rule. There's a meta thing that we think of as being the apply the rule, if you understand what I'm saying. Now, what I think you're doing here is to try to deconstruct that concept by saying that instead of having an apply the rule, you're instead saying you're going to do that with assignments like x equals thing of x. That's your way of defining. I mean, in other words, the generic evaluator would just be x equals eval of x. That's equivalent to, well, I think, do you understand what I'm saying?
Not yet.
Okay, so what I'm saying is the usual evaluator is like fixed, let's say you call the evaluator eval. Okay. Then saying x equals eval of x. The fixed point of x equals eval of x is x equals, nest to infinity of eval on x.
Yeah.
Okay. So I'm saying that you're saying you want a flexible way of representing an evaluation-like process. So what I'm saying is the existing evaluation process is nest to infinity of eval on x, which you could also write as x equals eval of x. So, you see what I'm saying so far?
Yeah.
But what you are claiming, I'm not sure I agree with you, is that you have a more general form of evaluation by being able to say, instead of just saying x equals eval of x, you can say x equals f of x comma g of x or something. That's a more general form of evaluation-like activity. But what you're doing here, you are describing an infinite data structure by self-reference, and then you're equating evaluation with some kind of end result in that infinite data structure, if I'm not mistaken. Is that correct?
Oh yeah, well, then by querying all the question you want to ask, you do by querying this data structure. Yeah.
Okay, but the whole point here is, normally in the language, we have, and in almost everything we do, we have the notion of there is an eval. This is where we went through again before, which is what we need. This, the thing where we've got replacement rules, we've got function application, and we've got this thing that you're now doing, which you're now conflating a yet different thing into this, which we were talking about, down value computation as a okay. When you say, what did we call it last time? We had multi-way nest, right? What did we call it? What were we calling that?
We have multi-way nest. It's
Okay.
basically lazy nest tree.
Yes, but multi-way nest takes you could write multi-way nest. If you wanted to write it as a self-referential equation, you could. What multi-way nest does, right? Multi-way nest is just x equals list f of x comma g of x, for example. Am I right? Well, in this case, you'd say x equals list x plus 1, 2x. Right? That's what that is, if I'm not mistaken. Correct? Yeah. I don't know where you put the 1 there. I don't know where you put the 1 that's the starting point for the multi-way nest. Where do you put that?
Well, let's think.
It would be like x equals lazy expression of tree of 1 comma x plus 1, 2x.
Okay.
Right.
Yeah.
Like that?
Yeah. No, still the list.
Yeah, right. So hold on. So what is that giving us now? So, yeah.
I think this is something slightly different because of the fact that the x's refer to the whole expression.
Yeah. Well, you have to stop at some point. So you may evaluate it, you write some traversal, then you get rid of these self-references. You basically finalize your tree, and then you can show it.
Okay, look. Do you understand what I mean, the point that I'm making is what we've got previously, multi-way nest, multi-way replace, they have well understood ways to move forward. Am I making sense? You seem to be defining a new way to move forward by using self-reference. Am I making sense?
Yeah, and it's more. It is more aligned with what other people are doing.
For better or worse, because they haven't managed to get very far in what they're doing. So I'm not that interested.
No, it's like for Haskell, it's like how it's working.
Yeah, I understand that. And but it's not that's not the problem we're trying to solve particularly.
Yeah, but at least some motivation is there, I think, worth exploring.
Up to a point. I mean, I don't get it. Okay, show me where, great, there's this amazing technology, and we'd like to understand the infinite data structures and make use of them and so on. But nobody's doing stuff with infinite data structures for real that I know of. There are, yes, in principle, you could have that, but it's not something where we talked about this multiple times. We've talked about canonical forms problems. We've talked about a bunch of other things. I don't. Okay, let's go through this again. What are we really getting here? We've got something where, I'm sorry, I really don't understand. I don't understand what the point of this is. Other than,
we're trying to define some kind of paradigm to work with, to better work with this kind of infinite data structures. And
all right, okay, fine. But so then what you're saying is, okay, see, this is where I think one is getting confused. All right. One way of parameterizing an infinite data structure is through self-reference. It is certainly not the only way of having an infinite data structure. It is one way of parameterizing it. Am I making sense?
Oh yeah, basically it's a graph. And the whole computation on it boils down to graph reduction.
Well, fine, but let's imagine you have a combinator expression, okay? And it's going to, as you evaluate it, it's going to generate an infinite sequence of combinator expressions. Okay. So is that easily representable here? For example, the non-terminating S combinator expression, is that easily representable here?
Maybe if we can just define it like this and make it a lazy expression. Oh, what is it?
I always have to look it up, which is embarrassing. But it's that of y of x, isn't it, or something? I forget which order it's in.
Yeah, well, it's something like this. Oh.
Okay, so I can look up. Hold on.
I don't know. Just
I'll look up what the actual expression is. No, it's x of z of y of z, by the way. That first thing, x of z of y of z. Okay, and now the first non-terminating S expression is, okay, I'll put it in, I'll send it to you. There's two of them. Now you can take one of those. Let's take the first one of those. Okay, that should be a non-terminating thing.
Wow.
What's that?
Oh, it died.
Maybe it died. What died?
It goes into an infinite loop again. Yeah, well, it's hard to control.
Yes, I know. That's why I don't think this is so useful. Because the whole point is, I mean, again, to give the meta lecture about language design, right? The goal of language design is have people do things that work.
So we just have to make it better.
No, I don't think that's correct conclusion. I'm sorry, I don't think it's the correct conclusion. I think it's the type of mistake that was made with Prolog, for example, where people routinely define things where it would just go off into la la land. And that's why it never really worked in practice, is because the, you define something which is, explosive, right? And whenever you do that in language design, it's just a bad idea. So let's go through this again, right?
Well, it doesn't mean it's wrong. It's like, okay,
it's not wrong. It's just not useful, right? I mean, so you can define a lot of languages that are not wrong. I mean, the whole point is to define something that is what we're really trying to do is we're trying to have a way so that people like us can use multi-computation in practice. Right? So as soon as we have something where every time you press the wrong button, the whole spacecraft explodes, it doesn't really work very well. Right? We want something where, it's like you could imagine something where you have an airplane And, you know, the controls do things like, you know, what's a good example? I mean, maybe I'm too airplane specific, but I mean, in I don't know what, you know, you want controls where most of, you know, the easy to control stuff does something that's actually useful, turns the airplane, things like that, rather than that the easy to control thing puts it in a tailspin. If you understand what I'm saying.
Well, it's clear that we have to come up with the easy controls, but it's not like find replace path is gonna be this easy control that solves everything.
No, I agree, but I think it's useful. It's understandable. It's useful. There's a whole class of problems that it can deal with. Right? So what you're doing here is you've got potentially a sort of super powerful thing here where most of the time it's just going to blow up. Right?
Well, if you click the buttons, maybe. But the point is to have the code like find replace path that it's just a data structure. It doesn't have to be some interactable thing at all.
No, I understand that, but what I'm attacking here, and I think, you know, given that you're studying this, right? Let's see if we can turn this into something that is more useful. Okay. What you're saying is one way to represent the progress of computation is through self-reference, right? X equals eval of X. That is a way to represent the process of infinite evaluation. Am I correct?
Well, usually that's how it's defined.
Yes, I know. But that particular, okay. The question is, do you want to change at the level of the self-referential structure? That is a way where unraveling the self-referential structure is equivalent to a time sequence of evaluation. Am I making sense? Because the self-referential structure is not a time sequence. It's just a self-referential structure. Does that make sense?
Well, yeah, you can have this structure, which is a graph, and the reduction would be, it can be represented as a state in the multi-way system itself, so that you can evaluate it in different orders.
What's a multi-way? What's part of no?
The lazy expression here, or the self-referential graph that you want to reduce, is a state in the multi-way system, right? When the transition is going to be evaluating some of its part, maybe resolving some self-reference.
Okay, so there's one way of doing this that we actually considered in the physics project, and I have an incredibly obscure note in the technical introduction to the physics project, which says you could consider encoding the whole history of every state in a state. You see what I'm saying? So in other words, when you get to, for example, instead of having an atom of space called 13, that atom of space could package inside it the whole provenance and lineage of that atom of space, where it came from, so to speak.
Yeah, it's history.
Right. If you do that, you do not make any progress. The universe will never progress. All it is just a self-referential structure that, you know, is not particularly useful, because any observer of it has to resolve it to some extent. You know, seeing it in its self-referential form. Okay, so the issue would be, you could say, oh, but it is a more useful definition. I mean, you could imagine, I don't think it's true, but you could imagine that the right way to represent multi-computational processes is implicitly by virtue of their, what in physics might be called self-consistent equations. Am I making sense? I don't know how physicsy, we have a few physicsy people here, but I mean, at least Jose probably, I mean, to go physicsy, like the beta salpeter equation is a good example of this, where you're representing a bound state and you're saying the bound state is equal to some operator acting on the bound state. Maybe that was not useful for anybody, but But that's there is a motif, this idea, the Schwinger-Dyson equations are the same way in physics. They're these self-consistent equations like that. Generally, those things have not been very useful. I mean, they're a representation and they're kind of neat. They're like generating function type thing. They can be, they're not like generating functions, but they are, you can kind of unravel them like generating functions, if that makes sense.
No, this kind of thing you also can unravel. You can imagine solving an equation when you resolve the self-reference.
I know. I'm saying that the history of such self-consistent equations is, at least in physics, isn't, I think, not particularly good, right? And I think in this computational setting, it seems very questionable. I don't know. Maybe it's useful. It's usually hard for people to understand, blows up easily, and isn't a good representation, I think. But convince me otherwise. I mean, like for example, let's imagine that you had a theory of infinite self-referential data structures, okay, that was based on these things. It would be like saying, we could translate to transfinite numbers, something, the expression x equals f of x could be some kind of thing that, where you say, what is the length of, or the tree version of that, right? X equals f of x comma x. Okay, can somebody else help me out here? I think this is not a good branch, but I don't know. So I mean, I think we have a definite branch to follow. I don't think this is a good representation of multi-computation. I think it is not a useful for humans representation, but I might be wrong. And the fact that whenever we do an example here, it blows up is not a great sign, because that's what I would have expected would happen, right?
Well, I wouldn't cling to that particular blow up.
No, but I understand, but I'm saying to you, I don't think, okay, you can make these things that are self-referential, objects that are defined by self-reference. Okay. I just don't know how to make those. Unless you have a Cantor-like representation of the result of a piece of self-reference like that, unless you can symbolify the result of the self-reference, I don't think it's going to work.
Well, resolving a self-reference is basically how all the lazy expressions are resolved. You just strip away the necessary parts that you need.
I know, but I'm saying that having this general case of self-reference, I don't think is going to be useful, because I think that the majority of cases people will define will just blow up.
Well, I'm not necessarily agree with that. Because
okay, well then show me some examples.
We have a precedence of a language of Haskell, like every data structure, useful one, is a self-referential one.
Okay, Christopher, can you make a comment about this?
I don't know. I mean, I just think that the more concrete, lazy lists and so on is just, it's much more clear what to do, and it's much more clearly useful than if it's everything is just this sort of unstructured, maybe self-referential noodle soup.
But I mean, let's try to understand what we can get. Given that you've done a whole bunch of work on this, let's try and figure out what we can learn from it. Okay? And simply saying it should work because it sort of works for Haskell, I don't think is really that useful. I think what we need to understand is, okay, we know we're trying to represent certain kinds of things in terms of multi-computation. I don't know, is James here?
Yes.
Can you comment on, I mean, if you look at this and you imagine this in terms of Rooleads and N machines and all this kind of thing, is this going to provide a useful representation of any of that stuff?
It's hard to say, because personally, the design of it at the moment is somewhat of a barrier. It seems to prohibit or impede some understanding on my part. Maybe this can be presented in an easier way, but it's hard for me to follow it.
Let me just cut this back again. This is okay. In physics, for example, this is a pretty common idea that, maybe Jose wants to comment on this. It's a pretty common idea to make up self-consistent equations for things.
Fine.
Jose, do you want to make a comment on that?
I know this is done in quantum mechanics, but it's not that familiar to me.
Yeah,
I guess you're referring to bootstrap methods and things like that.
Yes. It is a form of, the most common cases are things like the Schwinger-Dyson equation, the Blythe-Salpeter equation. They're all of the form x equals f of x. They are, for example, very typical cases of bound state. Okay, particles bound together, and the concept is, your atom is your atom plus one additional virtual photon exchange, for example. In other words, atom equals atom with a virtual photon exchange added. And the definition of atom, the bound state atom, positronium, whatever the heck it is that thing that you get that solves the equation x equals f of x. Okay?
Yep.
And, it's, by the way, let me think. I'm trying to remember in the original, in kind of, how does that relate to the diagonal argument well, anyway, it's a thing where people do this. They say we will define self-consistently x equals f of x.
I guess you are then interested in finding some sort of fixed point, a solution of the equation.
Yeah, exactly. But the whole point is that what we're doing, okay, you can think of the whole operation of Wolfram language as solving the equation x equals eval of x. That's what we do, right? We're solving that equation. But our representation of solving that equation is much more the unraveled fixed point of eval operating on blah, blah, blah. You see what I'm saying? And it's just a question of how you represent it. And this is why I'm asking Nick to justify, because you can do something more general than just x equals f of x. You can do much more complicated things here as you're doing. X equals f of x and all kinds of stuff like this. So what I'm trying to understand is, there is a model of doing this, which is a fixed point single way computation, which is x equals f of x. You've got a different form of evaluation here that's something more complicated, and I'm trying to understand what that's good for. Nick.
Well, it's hard. Well, if we could actually solve such equations like this one, so in principle, there could be some solver that given a lazy expression with self-reference, it may be some operators like that actually come up with a solution, closed form. But it's not general is the case.
I know. This is what I keep on saying. This is what, look, if we could invent an analog of transfinite numbers to be transfinite expressions, right? Then we would have solutions to a large class of equations like this. Am I making sense?
Yeah.
But the theory of transfinite expressions, which I don't even think that term existed before a minute ago, is we don't have a theory of transfinite expressions. And what you're saying is, what you've got is a very delicate, fragile representation of transfinite expressions.
We did discuss something like that in the past once, in relation to the join of two infinite lengths. So how to refer to the position of the first element of the second list.
Yes. Right. I mean, that's a very basic transfinite expression question.
Well, this is kind of an example of that. So I can have built-in just for the length case, how to represent some kind of transfinite number. If you have an infinite list, then this would be
What on earth is that?
like how this is represented.
What is NAT?
It's like a special wrapper that, well, a special type that length is returned so that you can do like feed it again to the range. So if you have an infinite list and you want a length of it, it will return a NAT, which can like iterate, unwrap this infinite list again, so that you can construct, even use it, construct a new range, for example.
Although it seems like the NAT, either it's going to be a finite range, in which case you could just represent it with a pair of integers or 3 integers or something like that, or it's going to be infinite, in which case if it's anything other than what aleph 0, you're in trouble, right? Because it doesn't make sense to have an uncountable range.
Well, I understand. With range, yes, I understand. There's a complication here because the content of the range is ordinals. The length of the range may be cardinals, but the content is ordinals.
Well, no. But the point is you can't have an uncountable lazy list because it has a first element and a second element and a third element.
Sure.
So,
no, but I'm saying that the element, you can imagine. This is where it's confusing between cardinal and ordinal numbers. The actual elements of the infinite range go to omega, omega squared, epsilon 0, blah, 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 right? But if we say, how long is that list? The answer is aleph 0. And if we say,
in fact how ordinals and cardinals work, yes.
Indeed. But if you say, I want to index into that list, I want to get, see, this is where I'm now totally confused. Let's say I want to have a part extractor that extracts omega squared. What the heck is the part that you give? Because the part you should give should be a cardinal, shouldn't it? And yet there is no
cardinal. Cardinal is a size. I mean,
it's an ordinal.
The part that you give is just a value, right?
No, but they are ordinals. So parts, because they are ordered, they are ordinals. So the element that we were discussing would be omega.
Yeah.
And there is this question that omega plus 1 is not the same as 1 plus omega.
Indeed. Right. But you're saying that I can give part numbers, I could give transfinite part numbers.
Right.
But the bigger thing is, this is actually a little bit analogous to, there was a summer school project that was vaguely related to this. I mean, where there was the issue of basically of a set of things. I think it was the fusible numbers, and you have to you want to be able to basically ask for the omega squared fusible number or the omega plus 1th fusible number or whatever. But I mean, as though I think will be the case in most situations like this, even if you have a way of representing the transfinite index effectively, there isn't really a general way of being able to then, if you just have an expression for like it's easy to write an expression where you say you give me the nth, where n is an integer, thing, and I'll give you a value for it. It's hard to then say give me n where n is any sort of transfinite ordinal and I'll give you a value. It's hard to express that function.
Yeah. Well, okay. Look. Okay, I think we probably mined this about as far as we can right now. I'm not. I mean, I'm fairly confused how this fits in to. I mean, as a piece of language design, I understand what this is. The experience with such things in the past, my experience with such things has not been very good, but. There's always a look. I mean, for many years, I didn't believe in associations because the experience with associations in S&P was bad. So it doesn't mean that it's necessary just because it's been implemented badly before doesn't mean it's a bad idea. But I don't really get this. I don't see how one's going to turn this into. I mean, what we're trying to do with multi-computation right now is, if we think about it in chemistry or in economics or in one of these other areas, we're imagining what are the programming elements that we want to use to represent multi-computational kinds of things, just like in, okay, so here's a question. I don't really have all these analogies properly understood. Cellular automata turn out to be a pretty good minimalized model of kind of parallel computation, single way evaluation. There are a zillion other things you could imagine that are just like I take various pieces of data and I munge it up and I get the next thing. They're not as useful. For multi-computation, we have the kind of the strings case, we have the numbers case, we have the hypergraph case. But if we want something that is a more structured example of multi-computation, that's kind of what we're doing by saying expression-based multi-computation. And again, how does one go multi? Answer. Number one, we have sort of the multi-way nest case. We've got the multi-way replace case. We've got the implicit multiism from pattern matching. And I'm just, I don't know. I mean, maybe there's a way. I'm really confused here. This is, the other way to go multi is to say my fundamental evaluation process is defined by some essentially multi, self-consistent equation. So I think what you're doing here. Is that right?
Well, it's close, yeah. If you actually have an applied problem that you want to solve, that's what you probably.
Yes, but I mean, this is the point that I mean, do we believe if we are thinking about the Rulliad, we're thinking about N machines, we're thinking about I don't know, theorem proving, we're thinking about metamathematics, we're thinking about chemistry, can we think about those in terms of these self-consistent equations?
I think we are.
I'll have to think about that. I mean, I've always been thinking about some of this in terms of functional equations. I'll have to think about self-consistent equations.
I mean, it's like functional equations, okay? The number of functional equations that can be solved in reasonable closed form is incredibly small.
Right.
I guess it depends very much on the properties of the F, whether it's a contraction mapping and it has fixed points and things like that.
Yes, I think so. But the problem is that while there might be a lovely fixed point theorem for certain cases, by the time you can do the general case, which is what Nick is showing here, of x equals f of y of x of et cetera, et cetera, et cetera, I just think it's very rare to be able to resolve that.
Yeah, that I agree.
And so I just don't get, unless we have a way of representing general transfinite expressions in a way, I mean, this is what, Roger has pushed extensively in, in things like, it started with algebraic numbers, it's then, differential root objects and things like this. His point is, it's trivial to just say, oh yeah, well, we've got a differential equation that we can't solve. Great. Just imagine the solution to the differential equation and call it foo. Okay, that's not very useful. What becomes useful is if you can have a nice canonical representation of foo, and you can combine foo and bar and so on, and you can start having a whole calculus around these things, then it becomes useful. Am I making sense? So just saying you can in principle define this thing as, oh, well, I'm going to call the solution to the equation blah, isn't very useful. Now, so if we could define a theory of transfinite expressions that represents relations between these things and ways to combine them and so on, like if you take two of these things, what can you do with them? Can you combine them in any way? Nick?
Well, it's like we did here, for example. Why not? This is we combine them.
Okay. Fair enough.
We just programming with lazy expressions. It's not a big deal. They can reference each other. They not evaluate on their own until you ask it or query it. So I think it's a very well-defined paradigm of programming in general, and it can be generalized to multi-computation. I think. Just have to think about it more.
Well, no. Wait a minute. Your main point is you're saying X is lazily defined to be blah.
Mm-hmm.
I mean, yes, all those definitions can be lazy. And then, I mean, yes, that's fine. I don't know how useful this is. Because as I say, most cases that I know of, other than toys, I mean, it's just like, okay, I'm with logic programming, for example, for like 25 years, people would show me this stuff. And it's like, oh, what can you show? Okay, we'll look at the n queens problem. Okay, yes, we can do that one. Look at this problem, that problem. And there were like four toy problems people would show. And then it's like, well, what else can you do with it? Oh, well, it always blows up in practice. And in practice, we just write regular code. So that's what we're trying to avoid here. It's not very useful to do things like that. So, there may be some great thing here. I mean, the thing that we have learned, the thing that came out with combinators, for example, is there are plenty of infinite combinator expressions, which we understand not at all what to do with them. Right? Like we would like to understand them, we just don't. Like the canonical forms problem. Are these two combinator expressions the same up to some, in other words, given two things, could we, for example, have a simplifier that says, represented in lazy form, these two expressions are, one is blah and the other is, 2 plus blah. Am I making sense? That will be useful. I think it's super hard, but it's useful. Right?
Right.
So, I mean, look, we really need to, we know we have some paths that lead to definitely useful things. It's fine to investigate this, but we just kind of need to know, I don't get it. I don't get how this is useful. I don't get how it connects to other things. Sorry. Is there something I'm missing here? I mean, yes, you can define it. I understand you can define this. But what, where will it be used? Where could it be used?
Well, ideally, it's like some kind of domain-specific language that you can use. Because it's like you can use it, again, in Haskell, you can, like, all the programming there is just with the same kind of lazy expressions that you do.
I understand. I know that.
Recursion, and you can solve problems in there.
Okay,
Maybe.
Give me an example of something impressive. And don't say you can generate the primes, because I know that.
Well, that's
something that isn't just a demo. I mean, look, to give you an example of this, which I've probably given 75 times, in SMP, I had a whole bunch of evaluation control stuff. And there was this one example of being able to do faster Fibonacci numbers using evaluation control, using recursion control evaluation.
Mm-hmm.
But that was the only frigging example. Everything else was just a toy.
Well, I think we will come up with the same kind of issue with whatever we invent. It's like you have to switch to the whole worldview in order to.
I know. So I'm asking,
Yeah.
I mean, the thing that we've done is we understand more about multi-computation now because we've got real examples of it. We've got plenty of real examples. So we actually, implementing multi-computation makes sense because we have a worldview around it. Okay? Implementing self-referential computation, we don't have a worldview around that at this time, and nor does anybody else. It's a slow process to get a worldview around something, and it may or may not be useful. I mean, to give a good example, transfinite numbers have been around for 140 years, and they're not widely used for practical things. I kind of feel like these infinite data structure things and transfinite expressions are a place where they might finally get used in practice, but we're not there yet.
Well, self-referential stuff is not the only thing that it's happening here, right? It's like lazy range doesn't, or lazy list doesn't self-reference itself.
I know, but lazy list is a different thing, which can be dealt with more pragmatically. I mean, in other words, you can sign up for this more general thing that is then just fragile and explosive and not useful, or you can sign up for something more modest. I mean, it's just like, we could have signed up for, in the original Wolfram language evaluator, we could have signed up for a multi-way evaluator from day one. Okay? It wouldn't have been useful. Nobody would have understood anything.
Well, how is it different now?
Because we understand much more about multi-computation now. I mean, this is what we're trying to do is we understand more about multi-computation. We're trying to leverage that to make a multi-way evaluator that is, now more comprehensible. And we have a better understanding. I mean, in the past, this question of, what do the evaluation fronts look like, et cetera, et cetera, et cetera, we just had no way to think about that. No way to think about it. We could just say depth first, breadth first. That was about it. Right? We at least now understand that that's related to things like reference frames and general relativity and so on. Okay, metrics and coordination choices and all that kind of stuff. Now, in principle, we could have understood that 40 years ago, but we didn't. Right? So that's the opportunity now to move forward on that kind of thing. But we don't have a way to understand the general self-reference thing.
How is it different from just programming with recursion? Like we have a recursion limit problems. So isn't it the same kind of thing? But here you just have an additional control over it. If you don't have a self-reference, this is iteration. Like this
but the whole point is, look, recursion limit is a mess. Recursion limit is a hack and the most interesting feature of that hack is it hasn't bitten our heads off, so to speak. In other words, there's been a hack in the system for 35 years, but most people don't run into it because most programming doesn't ram its, nose into that issue. Right? But if you define a mode of programming where every time you use it, you get rammed into something which is a big mess, it will not be useful. Right? We've managed to have a style of programming where, yes, there is a corner case where things blow up, but it isn't the general case. I'm just not seeing this. I mean, we've got an opportunity to actually take multi-computation. That's what I want us to be doing, to actually take multi-computation, which we now have a better understanding of, and make it so that it is usable for programming. This is something different that, yes, we could have had. I mean, it's just like when I first developed SMP and theoretical computer scientists said, your language is impossible. It's like, really? Why? Well, because you can define x equals x plus 1 and it will blow up. It's like, okay, that's true. Turns out, between that and Wolfram language, we've got 40-something years of experience in using these things. And the fact that x equals x plus 1 blows up does not cause the language to be unusable. Right? Except if you say the primary way you're programming is to walk right at the edge of the precipice of x equals x plus 1, then you're going to have something that blows up all the time and it's not useful. Right? So, I mean, the art of the design of the language is to make it so that most of the time people are not walking on the edge of a precipice.
Well, the multi-computation maybe it's quite on edge.
I know, but the whole point is we know we have methods for dealing with it that are not this, that allow you to make progress with multi-computation in a way that people understand. The goal of the language design is to not, if we push people to the edge of the precipice and then say, okay, now you've got multi-computation, but you're on the edge of the precipice, it's just going to fail. The goal is to give them multi-computation in a way so that they're not dangling, over the edge of the precipice. And that's what we were trying to get a design for, and that's why we've talked about it. I mean, I was not thrilled to have to introduce all this lazy stuff as part of that, because I don't think it's really to the point. I think it's something that seems to be necessary to make it work efficiently and so on, and perhaps necessary as a way to think about it. But, to throw in this direction just doesn't seem, it's just not going to work. At least I don't see how to make it work. I mean, maybe there's a way to make it work, but I don't see it.
What is the alternative? Define super functions.
Yes.
And this is the way of programming in general applied multi-computation.
No. Yes, the way to start is just like nest list and nest graph are useful functions for all kinds of things. Nest list is a useful, essentially meta modeling primitive for all kinds of things. All kinds of cellular automata, Turing machines, whatever else, they're all basically nest list operations. Okay, nest graph is the beginnings of a multi-computational version of that. Only the beginnings, not a very, as we know, it doesn't work quite correctly for that. That's what we want to generalize. Right? If we could get the thing that we talked about many times here, multi-way nest, multi-way replace, and so on, that's what we need to do, because that leverages the stuff we now understand about multi-computation and doesn't just throw us over this precipice.
I think we just should solve an actual problem before coming up with the design.
We have plenty of actual problems to solve. Let's
just focus on some of them.
No, but we know what we need. We've got tons of places where we've used our hackily built multi-way functions, multi-way system functions to do all kinds of things in the physics project, in this project, in that project, all over the place, right? The first step is to clean that up. That's what I've wanted to do for the last many months, because we know that that is a use case. It makes sense. It works. We just don't have a clean language design for it. In other words, just being able to get, branch shield graphs from, hypergraph rewriting, et cetera, et cetera, et cetera. That's already a useful use case. And the point is the use case for multi-computation is different from the use case for single-way computation. It isn't give me the answer. It's these more complicated things like give me branch shield graphs. Right? And the good news is, and the reason that I wanted to push this project, the good news is we already know what we want, because we've got hundreds, maybe 1,000 examples of actual, we made this picture, this is what we wanted to do. They're just not made in a very elegant way. Am I making sense?
Well, I still struggle to find one useful example apart from picture generation.
Well, I mean, you could take well, I don't know, you could ask something about, the confluence time or something, or there are all kinds of things which it happens that pictures are a useful way to represent these things. But we can, obviously, there's also computation, everything that we have in the function repository around multi-way system and its helper functions is what we're aiming for. A clean version of that is what we really want to do. That's the first step. Because those things, we know the output, right? We're not defining something where the thing is we know we're trying to do a certain class of computations. I mean, look, in my experience in doing language design, the thing you have to have is a set of computations you want to do, and then you figure out what is the elegant way to do those computations. We have a set of computations we want to do. We've got functions to do the computations. They're just not terribly elegant. And that's what we need to focus on. It's a good thing to explore. Is there a more general formalism? And I just don't think this one is working. And I think that it's nice, it's fine, but it's not the thing. I mean, it's, look, raw, arbitrary, unchecked computation is not human accessible. And you can define plenty of computation where humans just say, oh, I don't know what's going on. That's not useful language design. Right? And so, as I say, the main thing that caused me to want to do this project is that we have many examples now of actual useful multi-computational stuff to do. And that's what we need to get language design around.
Which is, it's most of the stuff we've done is just picture generation. It's like, even, it's like apart maybe from
Look, you can, whatever. I mean, it's the same thing. You've got proofs, you've got this, you've got that. You've got, find a number that satisfies this thing that is generated in this way. I mean, it doesn't, there's many computations. We've successfully defined plenty of computations to do. Yes, many of them generate pictures because a very common structure is not an answer. Okay, you can talk about computation, typical computation. Say, what do you want to generate in computation? Well, at times people said, I want to generate a number. I said, well, I want to generate a list of numbers. Well, maybe I want to generate a graph. It so happens that with multi-computation, it is more common to want to generate a graph, which we usually show as a picture, than it is to want to generate a number. But we could perfectly well generate numbers if we wanted to, and we have done in many cases. I mean, if you look at the stuff I did with combinations, there's tons of places where we generate numbers. If you want numbers out, it's not necessarily the most useful thing, but it's the thing you can do. Or you generate combinatorial expressions out. Anyway, look, I mean, this is why I wanted to get, this is why the original project was a clean language design for the multi-computational functions that we already have. And look, I think what you've successfully done here is to show a direction which is interesting. I don't think you have convincingly shown that it is a better way in any way to understand how to do this kind of computation. And I think we should go to what we were originally trying to do, which is to make a clean language design for the multi-computation that we already know we want to do. And I don't think self-reference is going to help us. I could be proved wrong, and you might have, in this meeting, you might have proved me wrong, but you haven't.
Yeah.
So, I mean, there may be something we're missing. There may be some great language design idea. I don't think there is. I think this is one of these ideas that's been around, like transfinite numbers have been around for 140 years, and nobody's, they just haven't quite landed. This is another thing that hasn't quite landed. Maybe in 50 years it will. But maybe in 2 years it will, but it hasn't yet. So anyway,
Still don't have any great ideas about design of those general functions that we already.
We went through the design months ago. We have a design, just needs to be implemented, and as we implement it, we're going to see lots of details. We have a design. It's this multi-computation, this computation object, et cetera, et cetera, et cetera. We have a design.
I mean, like that multi-object. Should we?
I think it's something. Let's not go. We're way over time here. Okay. Let's. I think this is Yeah, Memes is commenting that it's also relates to Jonathan's work on category theory. Yeah, I mean, yes, there are relations there also, and these string diagrams and so on are another thing, but they're all different. It's all different. But the focus, I don't think this focus on self-referential structures is right. Okay, I could be proved wrong, but I don't think it's right. All right, we should wrap up here. Anybody got any final comments? No. Okay. I really, really, really would like to see the things that we had designed several months ago actually implemented. I really, really want to see that happen. It's really kind of important that that happen. It's okay. All right. Let's wrap up here. Thanks. Okay. See you all soon.